So thank you very much, and thank Indranil for the invitation. And maybe people do this at the end of the talk, but I just want to thank the organizers for running a great first week of this workshop, and we should applaud, give them, and all the speakers also for great talks. So talk about the topology of the Betti moduli space. I guess I go through these first things, first bullets kind of quickly, but anyway, how do you cook up a character variety? You need to know some ingredients. So the first ingredient is some groups. So you have a finally generated group. I usually just pick some presentation, I usually think of fundamental group of some kind of manifold or orbifold or something like that. Probably in this crowd, a Kahler manifold. And the second ingredient is maybe a compact Lie group, which is a real zeros of some polynomials. We can look at the complex zeros of those, and any group arising in that way is a reductive affine algebraic group. And if we take a Zariski dense subgroup that contains the identity component of the real points in the real points, then I'll call that real reductive. Maybe that's not the most standard definition of real reductive, but that's what I'm going to mean by it. Certainly coincides with lots of examples, standard, or with different versions of the real reductive. So examples are everything you guys know and love. So with these two ingredients, we set up the Hom space. So we just look group homomorphisms, and the evaluation map defines an embedding into the R-fold product of G. It's generally not surjective, but if you have a free group, it is. But it does give a natural structure of an analytic subvariety. And if G is algebraic, then it's an algebraic variety, and in particular topological space. With respect to the real reductive groups, there's always a faithful linear representation. And so you could call this a representation variety. It's a subspace of representations of gamma with respect to a choice of a representation of G. Okay. So what do you do with that data? You look at the conjugation action on homomorphisms. An analogy with, if we were conjugating by GLV, these would be traditional characters. We're conjugating by G, so it's in quotes, not really a traditional character, but an analogy. And since we have a topological space, we can look at the subspace consisting of points with closed G orbits. And then I'm going to call the G character variety this just the orbit space. Okay. Polystable quotient. It's a non-trivial result of Richardson and Slaughty from 1990 that this space is Hausdorff. I guess just doing this polystable quotient generally just gives you a T1 space, but under the start with a real reductive group, we actually get a Hausdorff space, and it's complete. So in some natural affine space, it has all of its limit points. And if G started off as real algebraic, remember the definition of reductive did not include that. It could have been like semi-algebraic or something. Think like the identity component of GL and R. Anyway, if it was real algebraic, then this space actually has an additional structure. It's not just a complete Hausdorff space. It's actually semi-algebraic, which is really nice. And if it's compact, it's just the usual compact quotient. No big deal, just the usual conjugation orbit space. And if it was complex reductive, then the character variety is in bijective correspondence with the GIT quotient by G. So we inherit, the structure of a complex affine variety. And in particular, it's an algebraic set. And if capital G was GL or SL or SP or very, lots of other groups, then even though we're conjugating by G and not GL, the space is in bijective correspondence with traditional characters, and hence the name character variety. But in general, it's a bit of a misnomer. It's generally not a variety, nor given by characters. But in many cases, it is both. Let me just say, Adam Sikora and I are actually putting together a little tiny note to actually clarify this. So there's lots of people start with the ring of traces, and then look at the spectrum of that ring and get a variety out. And then there's also this construction, and they're not always the same. But there is a natural group action on one that relates it to the other. If you're interested in learning about that relationship, keep on the lookout. Sikora and I are going to have a new paper on the archive, hopefully in the next month, explaining how to do that, how to relate those two. Okay, anyway, this is a little advertisement. Okay, so where does the name Betti moduli space come from? Well, I mean, when G is abelian, this construction just gives you H1, and so, in analogy, this guy is often called the Betti moduli space, which I'm sure everyone knows. And at this point, everybody knows about the non-abelian Hodge correspondence. It has lots of incarnations. Here's one. That if you have a compact connected Kahler manifold and any connected complex reductive G, then this is homeomorphic and diffeomorphic on the smooth locus, but not biholomorphic to the moduli space of maybe pseudo-stable G Higgs bundles over X with some vanishing characteristic classes. But we've learned about this week already. Other forms exist, so in particular, if you look at the example of Riemann surfaces, you can, this is morally because of the vanishing characteristic classes, like a flatness condition, but if you want different topological types on the underlying holomorphic bundle, G bundle, then you can fix topological types and you can get a version of this theorem with different topological types of the Higgs bundle. If you want to learn more about that, just look at work by Garcia Prada, Goffin, and Mundet Rivera. Okay, and then the last thing, there's also some parabolic versions of this correspondence for punctured surfaces. So anyway, there's lots of incarnations of this theorem. Okay, so one way to think of a down and dirty way to think of Higgs bundles is you have a holomorphic G bundle over X, and a direction vector to that is your Higgs field, more or less, and you have to add some boundary divisors. It's not the cotangent bundle of the moduli space of holomorphic principal bundles, but that cotangent bundle is in the Higgs moduli space, and if you add in some boundary divisors in the right way to get a quasi-projective variety, then you get the whole Higgs bundle space. So since a Higgs field is generically, almost every Higgs field is a tangent to a principal bundle, you could naturally ask the question, since the cotangent bundle deformation retracts down to its base space, maybe this space here and this space have the same topological type. Maybe those boundary divisors are, topologically trivial. Who knows? Natural question. And so with that in mind, in a series of papers with Florentino and Casimiro and Oliveira, starting back in 2009 up until last year, we have this theorem. If you take any real reductive algebraic group, as I defined it earlier, let K be its maximal compact, and take gamma either a finally generated free group or an abelian group, a finally generated abelian group. I am allowing torsion there. Then there's a strong deformation retraction of this Betti moduli space onto this one. In particular, they have the same homotopy type. Now, you naturally wonder, does it generalize to all gamma? In particular, maybe the Kahler groups, right? But you can find counterexamples going back to Tia Bott and Hitchin. And Biswas Florentino showed, in general, using Higgs bundle theory, that for every Riemann surface of genus greater than or equal to 2, these guys are never homotopic. It's not just a few examples, they're never homotopic for closed surfaces. Okay, and they basically, the way they did that is, using the non-abelian Hodge correspondence, switch to the setting of Higgs bundles and holomorphic G bundles, and then over here in the Higgs bundle setting, they looked at the nilpotent cone, and then they identified a Betti number that was not the same in both of them, so they couldn't be homotopic. That's more or less how the proof went. So another thing you might be wondering is, who cares about free groups? Because free groups are never Kahler. I'd heard this, but I only learned the proof this week, because it's something I sort of remembered from conversations. But it's actually a really clever proof. I don't know if you guys know it. It's basically the first thing to note is that that the Betti number of the fundamental group of a Kahler manifold has to be even, because H1 breaks up into, right? So that immediately rules out if a free group was if you had an odd free group, it can't be a Kahler group, because the Betti number of the free group is odd. Yeah. So then what about even free groups, right? Well, the point is, if you had an even rank free group, say like 2R or something, then you could just map it to Z mod 2 by sending every generator to the identity except for one generator over here to the generator there, and then the kernel will be an odd rank free group of finite index. And then by covering space theory, because the Kahler form downstairs will lift to the Kahler form upstairs of a finite index cover, you would get a Kahler manifold with an odd rank fundamental group, which is a contradiction. It's kind of a neat proof. Yeah, I mean the proof that the kernel of this is an odd rank free group relies on some combinatorial form of subgroups. I'm not going to write. Maybe I won't write it down anyway. Of subgroups of free groups, the rank of subgroups of free groups. So it's not a hard one. Anyway, so why in the world would you care? Because free groups are not ever Kahler. Well, a first answer would be, well, every single Betti moduli space embeds into a free group character variety, and so the structure of free group character varieties imposes itself on all of these. So the free group character variety is a natural object to study. Maybe that's a little bit weak. Maybe it's not that compelling. I don't know. I find it compelling, but maybe not. Maybe a perhaps more compelling reason is if you look at open surfaces, so you take a Riemann surface and put a bunch of punctures in it, right? Now you have a free group is the fundamental group, and then when you fix the boundary data there, you get parabolic Higgs bundles, and so as you vary the boundary data, the free group character variety becomes a sort of master space that where you can look at deformations of parabolic Higgs through the non-abelian Hodge correspondence. And deformation theory on moduli spaces is very interesting. You maybe have one parabolic Higgs bundle where you know the lot about it, and you have another one that you don't know nothing about, but if you can create a deformation between the two, you can get facts about the one from the other. But I'd say the most compelling reason to care about free group character varieties, even if free groups are not Kahler groups, is that free groups sit into natural families of gamma, where a lot of Kahler groups sit. And if you want to understand general properties of these Betti moduli spaces, very often you're looking at families of gamma that all have similar properties. And sometimes the free group case is a case where either motivating or illuminating within the family, and some things in the family might be Kahler groups. And I have a couple examples of that coming up. Okay, so on the other hand, it's all about free groups. On the other hand, what did the last theorem say? It had free groups and abelian groups, right? Well, okay, so free groups, you might have needed some motivation, but abelian groups are great, because any abelian group, finitely generated abelian group with even rank free part is Kahler. Why? Because Serre showed that every finite group is a Kahler group, and you're looking at abelian varieties, right? C to the 2n mod Z to the 2n, right? You get even rank free abelian groups or Kahler groups, and then the product of two Kahler groups is Kahler because the product Kahler form, is the product of Kahler forms is a Kahler form. Okay, so abelian groups are very great examples of Higgs, where that deformation attraction theorem would apply to Higgs theory, right? So what does that say? You take the moduli space of Higgs bundles over a Kahler manifold with an abelian fundamental group, then it has the same homotopy type as the holomorphic vector bundle, where the Higgs field is 0, in other words. So that's one way to think of that theorem I just listed there in that case. Okay, anyway. So what's a sketch of the proof? I mean, both of there's 3 papers listed there. I'm certainly not going to go through any of it, but I'm going to boil down the 2 main cases to just a slide or 2, okay? So what's the basic idea for free groups? Well, what do? You first trade up the GIT quotient with, or the polystable quotient with a quotient by K, the maximal compact, and then you show that this guy naturally embeds into this guy here, and that basically is not too hard. You're saying that if you have 2 G equivalent by G conjugation K representations, that they're actually K equivalent, and that's a little calculation to show. It comes, essentially comes from the fact that K is dense, is Zariski dense in G. And then the top map is essentially the polar decomposition in each factor through the evaluation map. So this is a tuple of matrices, right? And then each matrix is deformation retracts to K. It's a K part because of the polar decomposition. So you have, G is K. Lie algebra of K times I, and it turns out the polar decomposition is K equivariant, so you get a nice deformation retraction there. That doesn't necessarily get you very far, but then the main ingredient is using Kemp-Ness theory. So Kemp and Ness, let's say G is complex reductive, showed that in each extended equivalence class of the GIT quotient, you could pick out a natural K orbit, and you can do so in a continuous fashion. Okay, up to the K action, okay? And then Richardson and Slowdy showed it also works for real reductive, okay? So basically, this is like I call a Kemp-Ness section. So it's, you're defining a setup here that whose quotient is homeomorphic to this quotient, but it's only up to K equivalence. So, and then the end of the day, you just go up, over, down, and that's your deformation retraction. I mean, you got to show the diagram commutes, and then you can construct this Kemp-Ness set in the right way and all that stuff. But basically, that's the idea. So that's free groups. Any questions so far? It's at the top level. Yeah. So we have. So you just have so because it's a free group, you just have a tuple of matrices. You have no relations. So yeah, that's a good question. So why can't you just do this like with any gamma, right? You would have to have the straight line deformation retraction by sending this to 0, preserve the relations defining gamma, and that just doesn't happen in general. Exactly. Any other questions? Am I going too fast? It's always a risk with slides. If I'm going too slow, I can certainly go faster, right? No? Okay. Okay, so the other case is abelian groups. And so with abelian groups, this is not going to work. So a new idea is needed. And so basically, the new idea is to cheat. So with abelian groups, the first thing you do is you say this doesn't make any sense. So this means the semi-simple elements in G. It's not a group. So this notation really is suggesting something that's not true at all. This is not a set of group homomorphisms because GSS is not a group. What does this mean? This means the set of homomorphisms from your abelian group A into G that have their outputs, if you pick a presentation for A, so we fix a presentation for A, find a set of generators, right? So that have each output of the generators semi-simple. Okay? So that's a subset of the Hom space, but it's not a set of homomorphisms. I mean, it's not the group homomorphism here to here, because this is not a group. Okay? But it's a subset of the homomorphisms. Yeah? But it is a subset that's preserved by conjugation in G. Okay? So it's a G stable subspace. Okay? So the quotient makes sense. And then what you show is because A is abelian, that this guy here is actually homeomorphic to the moduli space there. Okay? Now this is because A is abelian. This is false for free groups. It's false for most groups gamma. This is essentially saying if each factor has a closed orbit, then the whole tuple has a closed orbit, and if and only if, essentially. And that's just false in general. But because you're talking about commuting matrices, it's true. Yeah. Yeah, exactly. It's exactly the statement. Yeah, but it carries over, yeah, in general for reductive algebraic groups. Yeah. Okay, so the second thing you do is so both cases we're trading up these two spaces with something, an auxiliary space that we can work with better. That's the cheat. We're just saying, okay, these guys are hard. We can't really come up with a global deformation retraction like we did over here. So let's just get rid of them and trade them up for things that are easier to work with. Okay. So again, we do the same thing. This is not a group here. What does GK mean? GK is just all the G translates of K by the conjugation action. Okay, so it's a set. Okay, and these are and this is the set of all homomorphisms that have, again, with respect to a presentation, have their outputs in that set right there. Okay, and then it's a G stable space. It's obviously G stable. If like the outputs are all conjugate K things conjugate by G, then if you conjugate by G, you're still a G conjugate of K, right? And again, if you take this thing, you can do this with any gamma, and you could conjugate by G, and it's kind of like clearing denominators is what you want to happen, but it won't. So what happens, because A is abelian, you can essentially, in each factor, you have a tuple of things like this, G1, G2, right? But these are different G's, right? If they were the same G, then you could kill the G's by conjugating by the inverse. But with different G's, generally you'd have no hope to get rid of the G action, right? And just have it reduced to a K action. But because it's abelian, you can show that that there is a G that will essentially clear denominators. Okay, and again, it's just something to check, but it's just because it's abelian, and it's essentially the same thing as going on here. Because things are abelian, you can do things simultaneously that you normally would just be able to do one at a time. Okay, and then the trick is on the Hom space to show that this guy deformation retracts to this guy G equivariantly, and then you're done. And so how do you do this? Well, the main idea, it takes work. There's, especially because we're not assuming G's connected. We're doing this even in disconnected groups. Okay, so the disconnected issue is actually really subtle. It's, but anyway, the main idea is that semi-simple elements are diagonalizable, and so you can put in a common maximal torus, and then you can contract the magnitude of the eigenvalues, basically. Okay, but to put it in a maximal torus, you had to conjugate by G. So when you contracted the eigenvalues, you get into K. But then because you have to account for the fact that you conjugated to put it into your favorite torus, so that's why you get that G translate there at the end. That's the basic idea. It's more than that, but that's the basic idea. You have to show that all this can actually make sense in this generality. In SLN, it actually literally is that. But for a general G, you have to show that you can actually make sense of that. Okay, Anyway, any questions about the ideas of that theorem? Okay. So what do you get for it? Well, you get a lot, actually. So Tom Baird, in his thesis, calculates, this is just another notation for free group of rank R, so calculated the Poincare polynomial of this space. So the free group character variety for SU2. And he gets this nice formula, and he used equivariant cohomology. Now, that's great. I mean, but equivariant cohomology is not going to help you much for SL2C when you're talking about a GIT quotient. But given the deformation retraction, we get the Poincare polynomial for the GIT quotient, just for free, using a method that was not applicable to this setting. And we can keep going. So GL2C, is again by the deformation retraction theorem, is the same thing as U2, but then U2 relates to SU2 essentially by putting in a torus factor for each component. Okay, we can get SL3R, maximal, that's the real reductive example, maximal compact there is SO3, but SO3 is essentially SU2, but you have to quotient by Z mod 2, right? So you go back to Tom's thesis and you look at all those really complicated equivariant cohomology diagrams and you trace through the Z mod 2 action and you hope and pray and eventually you realize that the Z mod 2 is acting trivial in equivariant cohomology. And so this guy is actually the same as that guy. It's, you know, it's just a big diagram chase. It was really annoying. I had to ask Tom for help a few times. But it's true. So we're getting, but then we can go more. So U22 as a maximal compact of U2 cross U2. We already calculated the U2 one, so now we just square it. So we get the U22. And O3C has maximal compact O3R, but then O3R is related to SO3R by just having two components. So you get a 2 to the R factor. And then we know what the SO3 is the SU2, so we just get back to the SU2 part. And the list goes on. I'm not going to keep going, but there's lots of other examples you can get to. Okay. But we get lots of Poincare polynomials for lots of free group character varieties, just from one example, and this deformation retraction theorem. So a little bit, so that's an example of like using something, using topological fact in transformation groups, essentially, like compact group actions, right? And to get something about, you know, algebraic varieties and lots of examples. So what about the other way around? So here's a theorem about the algebraic geometric structure of this moduli space, free group rank R, SL2C, GIT quotient, and with my student, my ex-student, Sam Cavazos, we calculated the E polynomial. So the E polynomial is like to the mixed Hodge polynomial what the Poincare polynomial is to the mixed Hodge polynomial. It's just another specialization of that. This particular one, it has a nice number theoretic incarnation that if you look at, you can define this as a Z-scheme, and you can look at its the number of points over finite fields, yeah, and that function, if it's a polynomial, will be the E polynomial. And if it has that property, this is called polynomial count. And what we did is we showed this variety was polynomial count and by exhibiting the counting polynomial and showing it's a polynomial. I mean, sorry, the counting function is showing it's a polynomial. Okay? The neat thing, though, is if you evaluate the E polynomial at the field of order 1, I mean, you know, plug in 1, then you get the Euler characteristic, right? It's not really a field of order 1, right? I mean, just plug in 1. But if it was a field of order 1, it'd be the number of points on. Okay, let's just forget that. Anyway, so you plug in 1, you get the Euler characteristic, and we also get the Euler characteristic of the abelian character varieties there. Now, we also already knew the Poincare polynomial, so we could have got it directly. But anyway, Munoz and I generalized this to SL3 and got the E polynomial there, and there's a new Euler characteristic that wasn't known before. We use different methods, though, here. Sam and I literally stratified the space and counted points over finite fields. It was a really long calculation. Vicente and I used fibration techniques and sort of avoided the number theory stuff. Anyway. Okay, so what about homotopy groups? So that's a bit about deformation retractions. What about homotopy groups? Did anyone turn on the timer? The timer has not been started. So what time is it? I got time? Yeah, okay, all right. Let's put my clock here. So Dan and I have this theorem that came about from a really naive question. Dan and I were hanging out, and I said, "Hey, how does the character variety of G, the universal cover of G, relate to the universal cover of the character variety?" I don't know. It just seemed like, hey, maybe there's a relation. I don't know. So we asked the question, and this led us into a study of covering maps of character varieties. So basically, an exponent canceling group is an example of what I was talking about before. It's a family of gammas that includes both free groups and a number of Kahler groups, like abelian groups, free abelian groups, and also surface groups, and also twisted surface groups. It's a group that admits a presentation that has the property that, well, if you look at the abelianization, it just becomes free abelian. So basically, in other words, the relations all cancel out when you force when you force everything to commute. So let gamma be exponent canceling, and we're going to assume that that pi1 of G has no torsion, and take a covering homomorphism of the Lie groups. Then we get, the upshot is we get a covering map of the corresponding moduli spaces with an explicit form in the structure group. So a nice thing about that is it answers this question that that very often the universal cover of the character variety is the character variety of the universal cover. And it also gives you lots of examples where you can compute the fundamental group of the character variety, and it's just a product of the fundamental group of G. So in particular, if the character variety of the derived subgroup is simply connected, these hold. Okay. And this result is actually fairly sharp. You might wonder, is this torsion-free business, is that really needed? Or is that just a limitation of our proof? It's possible. But consider SU2 going to PSU2, covering map with structure Z mod 2. And let's suppose that our theorem applied to the situation where pi1 of G has torsion. Pi1 of that G has torsion. Okay? Then we get a covering map here with the structure group being the Klein group, which would imply that there's a free action of the Klein group on S2. Why? Because this group is S2. Is the two-sphere. So, of Z2 SU2. Maybe I'll do free group better yet. Let me do a free group to mod SU2. Is a solid ball. Looks kind of like this. But it's solid. That's what this is. And the abelian representations in there is the boundary of this. In particular, it's a two-sphere. Okay, and so we would have a free action on S2, if this was the case, with fundamental group, the Klein group, but there's no such surface. And moreover, you can actually check that this actually is homeomorphic to S2 too. That's not at all obvious, but you have to sort of, you identify the fixed points and break it up into pieces and glue it together, and magically, it turns out the two-sphere, the quotient of the two-sphere is still a two-sphere. But anyway, so if there's torsion in G, a covering map does not give you a covering map on the model. So the first place where it could fail fails. Okay. So, anyways, another corollary of the covering, of the existence of covering of the previous theorem, covering maps, is that you can reduce the study of higher homotopy groups of character varieties. So, under the assumption that that G doesn't have torsion and we have a covering map between H and G, then we get an induced the induced covering of moduli spaces gives an isomorphism for all higher homotopy groups by usual covering space theory. But this is nice. This essentially says if pi 1 of G has no torsion, then you can pick your favorite covering, and if you want to study higher homotopy groups. So what about the higher homotopy groups? Well, start at 0. So that's not higher, is it? That's lower. But anyway, start with the homotopy groups. So let's see. Ho and Liu recently showed that the number of connected components when when gamma is a fundamental group of a genus 2 or higher surface, where G is complex or compact, complex reductive or compact, is given by pi 1 of the derived subgroup of G. If we're dealing with an open surface group that is a free group, then it's always connected. So these are the three families I've been focusing on: surface groups, free groups, and abelian groups. So in the abelian group case, and when G is semi-simple, then the space is connected if and only if the following conditions hold. Gamma has no torsion. So if gamma has torsion, the space is disconnected. So gamma has no torsion, and one of A, B, and C, or C is true. Okay, so gamma has no torsion, and one of these is true. So if it has no torsion, then gamma is a free abelian group. So if the rank is 1, it's connected. If the rank is 2, G has to be simply connected. If the rank is higher than 2, then G not only has to be simply connected, but it has to be a product of simply connected groups of type A or C. And that's an if and only if statement. So that tells you when it's connected. And, when it's disconnected, you could ask how many connected components there are. And there's various things that you can say. I don't have a clean statement, so I didn't write anything. Yeah, this does come from Kack and Smilga's paper. At least part of it does, yeah. I mean, the theorem doesn't. The theorem is Florentino and myself. But we use Kack and Smilga in the proof of one direction of this. So one direction, it comes from Carlos's and my work and a result of Kack and Smilga. And the other direction comes essentially from looking at the cases rank 1, rank 2, so the one direction you have to show that if any of these conditions hold, then it's connected, right? So rank 1, I think, goes back to Steinberg, and rank 2, I forget who did it now. Maybe, yeah, I forget. And rank 3 or higher, showing that it's connected, comes down to showing that in the symplectic case and in the SLN case, the character variety for a free abelian group is in fact irreducible. It's not only irreducible, it's irreducible and normal, and then the product of those will also give you the same property, in particular connected. So that's one direction. And the other direction, that if it's connected, that it has to be one of those, then that Kack and Smilga's result is very important in that direction. Okay, so that's pi 0. Something we can say about pi 0. Okay. So now we're going to reduce ourselves to the connected component of that contains the identity, the trivial representation. Okay. So sometimes this is the whole space because the space is connected. Sometimes it's disconnected. It's one of the connected components. Okay. And then a theorem of Dan and Indranil and myself gives a nice theorem about the fundamental group of these moduli spaces. And what's amazing, and this is what I was referring to before, this is an example of what I was referring to before, that these two examples of Kahler groups, or that include Kahler groups, are all Kahler groups, sit in the same sort of family as a free group does. And indeed, this theorem did arise by the free group case first. The free group case came about first, the proof came about first, and then later, the three of us generalized that proof and included other groups. What's amazing is the result is uniform. It's the same answer in all cases. In particular, it says that if G is semi-simple, that the moduli space is simply connected. If G is semi-simple, then dG equals G. And this does not have any assumption on the torsion of pi1 of G, unlike the corollary from the covering space theorem. But it is consistent with that paper as a result. It better be, right? So we conjectured in the paper that this result is true for any exponent canceling gamma, any gamma that has that property before. But our proof has some uniform features for that. In particular, we show that if gamma is exponent canceling, that the natural map dg in G to G mod dg, if gamma is exponent canceling, that descends to a Serre fibration on moduli spaces for any exponent canceling gamma identity component. It actually also works with the identity component. Derived subgroup. And then using this Serre fibration, you can then using the Serre fibration, you can then apply, because it's a fibration, the long as x sequence in homotopy. Okay, and then in particular with pi1, you get pi1 of this, pi1 of this, pi1 of this guy. Now, and then over here, you get pi0 of this, which is trivial because it's connected. Okay, and then on this end, you get pi2 of this guy. But this guy you can show is a torus, so pi2 is trivial. So you reduce the proof to showing that this is simply connected. And then you get an isomorphism on pi1 here. And that's what and then pi1 of this is that. Because this guy is just a torus. Okay, using the decomposition for reductive groups, we get that this is dg cross a central torus mod f, where f is the intersection of this with torus, so it's central. And so when you quotient g by dg, you just get t, just t mod f. So, and this is a finite group acting freely on a torus gives you another torus of the same dimension. So it has the same. So because then it just the character variety just becomes effectively a product. Okay. All right. So you reduce it down to computing pi1 of that, and then the trick for that is the following. You set up this diagram. So you include. So this is for any exponent canceling gamma. Here, this is where we actually have to specialize to those cases. You look at the quotient. Then you take the quotient here. And this guy is contractible. And then you look at the inclusion of this group into each factor. So for every generator here, so you can think of this as a tuple of matrices that satisfy the relations of gamma. So you include this guy into the ith slot with a bunch of e's. And then for every generator of gamma, you have an I factor inclusion. And the statement is, if the image of all I of these maps generates the fundamental group here, then because it factors through a contractible space, that means that this has to be simply connected. Okay? But so the trick is to show that these natural inclusions generate the fundamental group here. But that, what? Yeah, DG, yeah, of course. Yeah. But that's not obvious. If gamma is a free group, it is obvious. With a little bit of work, if gamma is a free abelian group, you can show it. It's not obvious, but it doesn't take much work. What's hard is if it's a closed surface group. Now, we believe it's always true for gamma exponent canceling, okay? But we don't have a proof of that. But to show this for closed surface groups, we had to go, we had to work really hard and go to the space of flat connections, and it was a codimension argument, and it was the whole thing. But anyway, and in that case, we actually showed that this thing is simply connected, so of course it's trivially, trivially satisfies that property. But anyway, that's a sketch of the proof. That's the two main thrusts is getting the Serre fibration and then analyzing this diagram. And then this part was general for any exponent canceling gamma, and this part we addressed individually, those classes. Okay. So what about, that's pi 0, pi 1, what about pi 2? So with pi 2, Dan and I, when G is GL, SL, SU, or U, showed that pi 2 is always trivial. The naive idea is on the Hom space, it's a product of G's. And so pi 2 is always trivial because the G deformation retracts to a compact, and pi 2 of any compact is trivial. And so on the moduli space, you expect somehow that to be the, to descend. The problem, of course, is the moduli space is highly singular. Singularities are awful, even in the free group case, so you can't really lift. There's no lifting. So basically, this all it turned into a very long paper trying to deal with the singularities. But the upshot was we got Bott periodicity on the smooth locus, which was really nice. So we got lots of higher homotopy group statements on the smooth locus, which is the same as the irreducible locus for these groups here. It's not always the same. Irreducible locus and smooth locus for the moduli space are not generally the same, but for these four groups and lots of other ones, in fact, it is the same. Generally, the irreducible locus form is an orbifold. And the orbifold locus is a bit mysterious for other groups. In fact, there's a brand new result just came out like a couple weeks ago. You're just computing the codimension of that for PSL when n is p. I mean, n is a prime. So that's just to give you an indication. The first place where you would get a non-trivial orbifold locus, it's taking a lot of work just to compute the codimension. Anyway, okay, so I'm not going to talk about the proof of this, but maybe I'll say something about what's going on here. It's very, very little. Yeah, I think I got just a few more minutes. So suffices to just consider one of the four families of groups, SU. Why? Because we're dealing with free groups here, and by the deformation retraction theorem, GL is the same as U, and SL is the same as SU, but the difference between U and SU is just essentially a torus, and pi 2 doesn't kills the torus, so SU is enough. And we also can have, we want to assume R and N are, big enough. The cases of R and N that don't satisfy this inequality can be handled by hand directly, just because we can compute the examples, and it fits the theorem. There's no problem. In particular, the 2-2 case is known as the Frick-of-Vogt theorem, or in this case, is that with SUN, it's just this, the 2-2 case, and that's contractible. It's a ball. That's the most non-trivial of the ones being excluded here. Okay, so So the real trick is to show that we can get rid of that we don't care about the rank. Basically, that's the first main thing. That somehow the rank of the free group is, the result is uniform in the rank of the free group. So we set this diagram up here. We look at the smooth points of the moduli space, or if you like, the irreducible locus, the irreducible representations. And I have these maps here is surjective maps, but it's not at all obvious as a surjective. In fact, that's like a huge amount of work. But anyway, the basic idea is a free group of smaller rank injects into a free group of bigger rank, and so we get a map that way. And here, this is just inclusion a priori, without the pi 2s. I mean, just as on the moduli spaces. And then again, because a free group of lower rank injects into a free group of bigger rank, with respect to the moduli spaces, we get just an inclusion there. And then we take the diagram of moduli spaces and apply pi 2. You get a commutative diagram. Okay? So that's where you start, and there's nothing, nothing, at that point. Okay? But the first thing to do is to show that this top map is an isomorphism. And how do you do that? Well, you compute the codimension of the irreducible locus. And you can do that because the reducibles are, the reducible locus is given in terms of parabolic subgroups. And you can, and given that description of the reducibles, you can explicitly compute the codimension. And you can show it's sufficiently high. And then you can, because we were dealing with a smooth manifold now, we can, and we have a high codimension subspace, so we want to homotope off of, we can actually show this as isomorphism. It comes down to really this. So if we just, so this really should be not that. That should be, I mean, it is right what's written there, but there's a deduction. So you get the irreducible representations, FR, SUN, okay? That's what's there ahead of time. But because of the high codimension and transversality, we can show that that pi 2 of the irreducible representations is the same as pi 2 of this, and that is just the R-fold product of SUN, which is sitting here. Okay? So the transversality and a codimension count allows us to replace pi 2 of Hom of the irreducible locus with pi 2 of just the product of Lie groups. But this guy here is trivial because it's pi 2 of a compact Lie group, right? So we just have an isomorphism here. But this is, so this guy, independent of R, is isomorphic to the same thing. And that effectively shows that these guys are isomorphic, because they're both isomorphic to the same thing there, and you have to show that that commutes, that little triangle that's not written there, but the top thing on the triangle is this. Okay? So this is an isomorphism. Now, why in the world are those surjective? Well, those are surjective because this map here is 2 connected. Now, that statement comes from a more general statement of just CW complexes. Okay? So if you have a CW complex and a subcomplex, and you have an inclusion map of complexes that satisfies 3 properties. 1, the complement of the subcomplex is dense. Locally, if you have a neighborhood around say, a point in the subcomplex you're removing, and you now take out the subcomplex from that neighborhood, it stays path connected, and it's simply connected, then the inclusion map will be a two-connected map. In particular, pi2 will be trivial. So you have two local homotopy topology conditions and one sort of global condition, and that implies a global condition. And that's true in the context of subcomplexes. So the proof here comes down to showing that there's a nice subcomplex structure. This is a subcomplex of this, and that these conditions, in fact, are satisfied. The irreducible locus is dense, is easy, but then and B comes essentially from C. But showing that locally you can find neighborhoods when you remove the reducibles from it, the complement of the reducibles locally is simply connected and connected. That took a lot of work. We needed to come up with a local model of essentially the tangent space using a slice theorem, and using that got a local a model for the local neighborhoods, and then we had to analyze the connectedness of stabilizers in this context to show that we got and then a path lifting argument to show that the neighborhoods, were simply connected. We don't need every neighborhood; we just need the exist neighborhoods that have these properties. Okay, that was a lot of work to show this, but anyway, that's what we did, and then we proved this general result about CW complexes in the appendix that worked for any set of any complex. Okay, and then we applied that to this context. So, because this is a two-connected map, that means that this is surjective. So we have this diagram here. Now, isomorphism, surjection. Now that implies that that we get a surjection down here. And it's not hard to show it's one-to-one. Okay, the hard part is showing it was a surjection. Okay, so we get an isomorphism here. So this reduces the problem. So this essentially says we can just pick any R we like. That's 2 or more. So it reduces the problem to R equals 2 and n greater than or equal to 3. Why? Because we can compute the Fricke-Vogt theorem when n is 2 allows us to show that, or this guy here, this is contractible, and so pi2. The statement says if you figure out R equals 2, then you figure out all of them. So when n is 2, we know that pi2 is trivial, so now we know all the rest. So, and in fact, for n equals 3, we know the same thing, because a theorem of Florentino and mine shows that when n is 3 and R is 2, this is an 8-sphere, and then so pi2 is also trivial. So really, we just need to prove for R equals 2 and n greater than or equal to 4 that this space is trivial. So how do you do that? I don't have enough time. But basically the idea is we construct an explicit automorphism we construct an automorphism of pi2 of the space that factors through the R equals 1 case. What? You think it's 3? I thought we know, because we handled the 2. We had the R is 2, I think. Yeah, no, we needed R. It's R is 2. Yeah, it was R is 2. So again, what we did was we constructed an automorphism of pi2 that factors through this. But this guy is pi2 trivial, because we can this is homeomorphic to the exponential of the Weyl alcove. So in particular, it's contractible. Okay, so pi2 is trivial. So now we didn't take any old alpha. We constructed a very specific alpha And in fact, how did that happen? That was a really neat idea of Dan's, actually. In the free group case, the moduli space the homomorphism space is just a product of the groups. So it itself has a group structure. The Hom space itself is a group. That's not generally true. So somehow the moduli space remembers like a shadow of the group structure it came from. And so that sort of memory of the group structure of the Hom space, using that, we exploited that and constructed a very clever automorphism here that was able to, that factored through this. So there's like 2 copies of this, and it goes down and up. Okay? And anyway, so if we have an automorphism, again, we construct it a priori as an automorphism, and then we secondly show it factors through this case. Okay? So it factors through something trivial. It was trivial as an automorphism. The only way that's possible is if this was trivial. The end. I think I'm out of time. So a final remark is, so with the pi1 case, pi1 computation, we got that there was a uniform answer across closed surface groups, free groups, and abelian groups. But with pi2, it's not the case. We don't get a uniform answer. So what we showed with free groups just now is that the pi2 is trivial. But here's an example of a free abelian group where pi2 is not trivial, because it's a 2-sphere. But moreover, you can actually use this and look at the stable moduli space for closed surface groups, and you can show that the stable the stable moduli space is has pi2 equal to, or sorry, the space is CP infinity, but pi2 CP infinity is not trivial, and so that means that for every closed surface group there is some n. You might have to be a big N because we just know that stably it becomes a non-trivial, but that for some n this guy is non-trivial for closed surface groups, for every closed surface group. So pi1 the same in those 3 families. Pi2 is different in those 3 families. But anyway, so that's a bit about the homotopy groups. Thank you for your attention, and I'll end there. I see. Well, I'm sorry. NN. So for which no, not that I know of. We use compactness. We were definitely. You mean here for the pi2 statement? Yeah. So yeah, I guess we did. I don't remember exactly what they were off the top of my head. So there were some corollaries about that. I don't, but the proof we use, we're definitely using compactness for the local part of it. Yeah, because we were using the Kahler conjecture and Mostow slices. We had some idea in the complex case we might be able to replace the Mostow slices with Luna slices, but there were some technical issues. I mean, I feel like we were on the right track, but then we decided it was better to go with the compact groups because with the Mostow slices you get an honest slice. With the Luna slice, you sort of have everything related through étale maps, and then because we could pick which one we wanted because of the deformation retraction theorem, we just went with the one that was easier. But for real groups, I don't know. Is there an étale slice theorem for real reductive groups? I don't know of one. Yeah, it comes down to these local topology obstructions. So we sort of need these maps to be too connected in that picture that I had up there before. Yeah, so the existence of these neighborhoods are very special here. So neighborhoods so you're saying even around the singular locus. So every point I mean, so off the singular locus, all this is obvious. On the smooth locus, there's balls. You know what I mean? And and a codimension account is enough just to, I mean, you don't even need a codimension. I mean, you remove the thing off the singular locus, you remove the singular locus, the ball's not affected. And still it's contractible, no problem. The issue is on the singular locus. You take a point in the singular locus, then you want to remove the entire reducible locus on a neighborhood that you constructed around the singular locus, and you want to make sure it doesn't separate, and that if it was simply connected originally, that it stays simply connected. Now, the neighborhoods around singularities are going to look like cones. I mean, there's nice models of them, both in the compact and complex case, which look like cohomology groups, like quotients of cohomology groups. But I mean, we can compute some of these in both cases, and they look like, for like SU2, it's like, or SL2, let me say, it's like it looks like a complex cone, SL2C, a complex cone over a product of projective spaces, or something. Then you can use that explicit answer, then you take out the cone point essentially, and then you can show, hey, look, it's simply connected, it works. But then you try to generalize that away from this SL2C, just even SLN. And then the computations for the local models get much more complicated. I don't think it's known what the homeomorphism type of these local neighborhoods are. If I had to guess, I'd say something like, for SLN, I would say it's something like complex cones over products of mixed Grossmanians or something like this. But I don't know for sure what the answer is. But anyway, these local the local topology is important. And we definitely use the existence of slices to do it. And so for real groups, I don't know. We did get some, as Dan said, we did get some corollaries because of the, here, because we can, look at some real forms and relate them to these guys and then look at like maximal compacts in those. But it wasn't like directly using the ideas in the proof. It was more like cheating, like I did with the Poincare polynomials. Any other questions? Okay. All right, well, thank you.